Howdy guys, we are getting into the last part of the year, and this last part of the year has to do with waves and sound. So we're moving away from Newton's laws, we're getting into waves, light, and sound. We'll see how far we get. Should be a nice change of pace, maybe nice for some of you to hear that we're moving towards the end of the school year. We're getting at the end of April, we got May left. So let's just get started with waves. The definition of a wave is a traveling disturbance that carries energy from one place to another. If you're taking notes, write this stuff down. Make sure you get it into a notebook or something so you could always review back to it for a test or a quiz or studying, or even when you're doing your homework. So one more time, a wave is a traveling disturbance that carries energy from one place to the other. The particles themselves don't move. A wave is only the energy that's moving as it goes through. So here's the deal. How does the wave start? And that's where people get confused. A wave has to start from a source. It starts from a vibration. And sometimes people think the vibration is the wave, but in a lot of cases it's not. So I got a couple of clips here that I'm going to show you. The first one is just this. It's a steel ruler. Steel ruler's on the side of a table. The steel ruler's gonna vibrate. And the reason I'm showing this to you is I'm focused on the vibration. This is a vibration. So you can see the ruler vibrating. Now what you can't see in this video is you cannot see the wave. The wave is traveling from the ruler to your ear, and it's getting from the ruler to your ear through the air. And we can't see air, so you can't actually see the wave. So in order to help us out with that, I do have a different video that'll show us the wave move. Now in this case, you actually can't see the source. You can't see the vibration, but right over here, you can see the wave, and you can definitely see the wave in this video. I think it's pretty cool. This is a soccer game, obviously, and what we're doing is we're seeing the wave in a stadium. And there it goes. So we can't see the vibration, but we can see the wave. And it takes a little while for it to jump up to where we are. Here it comes. And it is pretty cool. So we got both of those examples. In example number one, you could see the vibration, and in example number two, you could see the wave. So what happens when we blend those two things together? If I wanted to blend those two things together to show them to you kind of at the same time, it's going to be very similar to the ruler example, but I'm going to hit pause here for a second. I'm going to go big screen with the screen there. In this case, what I have is I have a classic example of a tuning fork. Ta-da! And I hope you can see the tuning fork vibrate. If not, I'll do something to help you out. But here you go. When I strike the tuning fork, that is the vibration, that's the disturbance. The tuning fork right now is vibrating, and you can hear the sound wave. So that the sound wave is the energy that's traveling from this to the camera, and then ultimately from your screen to your ear. The tuning fork's not traveling to your ear. This is the vibration. The sound is the wave. Now I can prove to you this is vibrating by, as soon as I touch it, it stops. That's because I'm stopping it from vibrating. And there you go. So kind of a neat little demonstration with the tuning fork. I got another one here. This is my one-string guitar. Anyhow, put my one-string guitar. I got an original song for you. I wrote it about my dog. So there you go. I'm going to play a little song for you. Ready? Here we go. The string, by the way, is the vibration. Sound is getting to you through the air. That's the wave. The name of the song is David Had a Little Doggy. I wrote this song about my dog here. So here you go. All right. And here we go. David had a little dog, little dog. Little dog, David had a little dog who chased the ball all day. Woohoo! Feel free to tip me later. I do accept 10s and 20s, always. So anyhow, let me put this stuff away. The thing that the sound travels through, that's a medium. And so far, in most cases, I've only used in one medium or so. I'm going to put that camera back where it goes. There we go. That's a little bit better. So the medium in the first example with the ruler was air. The sound was traveling through the air to get to your ear. That's the matter through which the wave moves. In the second example, the medium was the crowd. The wave was moving through the crowd, so the crowd itself was the medium. In the third and fourth case, with my song and with the tuning fork, air was once again the medium. Air doesn't have to be the medium. It could be all kinds of different things. I'll share that with you in just a moment. For example, a water wave, something that somebody surfs on, the wave is moving through the water. So sound can travel through solid materials. So it can travel through this desk. We'll do an activity with that later in this unit about how sound can move through things. Not all waves require a medium. There's a couple of different kind of waves. One's called a mechanical wave. One's called an electromagnetic wave. A mechanical wave requires a medium. And an electromagnetic wave does not require a medium. So here are some examples of mechanical waves. The wave itself, like I said, either a water wave or the wave that you do at a stadium, that's a mechanical wave. You could put a wave in a spring, where you shake the spring and the spring moves up and down, and when you shake the spring and it moves up and down, you're seeing the wave move through. An earthquake, that's a wave moving through the ground. Sound is a great example, and sound typically gets to our ears through the air. So here, this guy, this is kind of a really cool demonstration. Really simple. I'll let him explain it. Here we go.
Okay, today I'm going to be putting a Bluetooth speaker in my vacuum chamber. So what we're testing out here is how sound travels in air. So sound, unlike light, needs a medium to travel through. So usually we hear sound that travels through air. And inside the speaker, there's a little cone that's vibrating up and down really fast. And that makes high and low pressure spikes come through the air. And it hits our eardrum, vibrates our eardrum, vibrates some nerves, and we hear sound. So if this cone that's in the speaker doesn't have any air to vibrate against, what would happen? Okay, to visualize what I mean, I have my speaker hanging in the air here, because I don't want it to touch the chamber and vibrate through the chamber. I have some saran wrap over a bowl to make a diaphragm, and I have some salt on here. So I'm going to play a tone on my Bluetooth speaker, and it's going to make high and low pressure waves go through the air that'll vibrate the diaphragm and vibrate the salt on top. So I'm going to play a 600 hertz tone. You can see how the salt just vibrates all over the place. So what I want to do is see how this changes as we're pumping out air out of the chamber. Okay, let's turn on
So the bowl
800 hertz.
represents your ear. And if the salt is moving, that means that you would be hearing it.
About negative 0.4 atmospheres. The salt's still really vibrating a lot.
That means you would be hearing the sound. So you got to remember, we're hearing a motor in the background.
Negative 0.6. Negative 0.8. Looks like the vibrating is dying down a little bit. Oh, it's going away. We're at negative 0.85 atmospheres, and I don't see any movement. A little bit back there, a little bit right there.
Which basically means if you were in the box right now, you would not be able to hear that speaker.
We're not even at full vacuum yet, and the salt has completely stopped moving. So that means now, even though the speaker's still playing as loud as ever, still playing its 800 hertz, but we can't hear it at all. I mean, the diaphragm can't hear it at all. Okay, we're at pretty good vacuum now. Negative 1 is a full vacuum. You can see the salt isn't vibrating at all. If you listen really close, you can hear a slight hum. So that means a little bit of sound is escaping, maybe up through the tape and vibrating the chamber walls, and it's coming out into my ears. Maybe you can hear it. So now I'm going to let the air in, and we're going to hear the sound increase, and we should see that salt start vibrating again. Let's zoom in on it. Okay, I'm going to let in the air. Look at that. Okay, we're at full atmosphere again. See that salt vibrating? So once you let the pressure back in, the pressure waves from the speaker can start vibrating that diaphragm again, and our ears, so you can hear it too. So what this all means is that all those movies you see where you hear an explosion happen in space, if that were real, you wouldn't really hear an explosion in space. You just hear absolute silence.
There you go. If you're in outer space, you would just hear absolute silence. So here's almost the same exact video. It's just in reverse. He put the microphone inside the box, and he's going to make sound outside the box. I like this one better. I think it actually works out a little bit better, and it's kind of really cool. So let's give that one a shot.
So today you're going to be inside the vacuum, and I'm going to be screaming in air, and we're going to see if you can still hear me. Okay, first let's start off and see if you can hear me just in normal air pressure with the lid on.
Yep, I can definitely hear him.
Okay, let's see if you can hear me in the vacuum chamber. 3, 2, 1.
That sound you hear is the air being sucked out.
We're at 0.5 atmosphere, so half an atmosphere already. Going down. Houston, can you hear me? We have a problem. Okay, we are at maximum vacuum now, so let's see if we can hear me. Okay, I'm going to scream as loud as I can. Ah! Ah! Okay, I just scared the crap out of my wife, so now she knows what I'm doing. Can you hear me? Help, I'm lost in space! Can you hear that?
So basically what he was just showing us is that mechanical waves require a medium. In the case of sound, if you do not have air, you can't hear. Air is the medium that carries sound to your ears. So if you do not have air, you would not be able to hear that. Electromagnetic waves, on the other hand, they do not want to have a medium. If you have a medium in the way of an electromagnetic wave, it'll stop it. If there's an electromagnetic wave and something's in the way of it, it just stops. So there are several examples of electromagnetic waves. Here's, again, kind of a nice video that's going to represent what electromagnetic waves are. I'm going to let it play for a few minutes.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go, it is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across the spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum.
So there you go. A radio wave, it does not want to have a medium. So if you put something in the way of a radio wave, it's going to stop it. The remote control. If you have to point the remote control at your TV. If there's something in the way of between the remote and the TV, it doesn't work. Your cell phone, you guys know if you're inside of a building, it's hard to get your cell phone to work. When you go outside, the cell phone works better. These are all examples of electromagnetic waves.
Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now.
But here's the deal. We can't see any of these because no medium's required. Now, we can't see sound waves either, but they do require a medium. They require air. So if we could somehow like color the air or put something in the air, you'd be able to see those. There's nothing you can do to help you see these electromagnetic waves that's being talked about in this video. So here's a chart of the electromagnetic waves. These are the same ones that he just said. There's gamma rays, X-rays, ultraviolet, visible light waves, infrared, microwaves, and radio. If you had earth science, you've seen this chart before. If you've been in chemistry, you've seen this chart before. This is one of those things that kind of crosses over. It's obviously kind of a general topic. It's global because in many science classes you talk about it. So up here I have the wavelength. We're going to talk more about that term in our next unit or the next lesson. But you can see the wavelength there. This is 10 to the third. This is 10 to the minus 2, 10 to the minus 5. So clearly as I'm moving this way, they're getting smaller and smaller and smaller for the wavelength, down to 10 to the minus 12. And down here, this is frequency. So part of your homework tonight, I'm going to ask you some questions about frequency, like what would be the frequency of a molecule vibrating? And then when you look at this, well, you're either going to say 10 to the 16th or 10 to the minus 8th, but if I'm asking you about frequency, you're going to write down 10 to the 16th for your answer. If I say, what is the wavelength of a butterfly? Well, a butterfly is not quite here or here, so if you said 10 to the minus 3 or 10 to the minus 4, that would be totally fine. Okay, so your homework tonight is going to be reading some numbers off of this chart. In addition to these two types of waves, because so far I've introduced you to two types of waves. There are mechanical waves and electromagnetic waves. In addition to that, there's something called a transverse wave and something called a longitudinal wave. So a transverse wave, that was what they just showed you in the video a minute ago. There are going to be some crests. Those crests are the high points of the wave, and there's going to be a trough, and a trough is a low point of the wave. if you go out here and take a look at this, there you go, transverse waves, super duper simple. Here's a crest. Here's a crest. By the way, the medium here is the spring. We're watching the wave move through that spring. A longitudinal wave is something called a compressional wave. So in this case, the direction of the wave and the wave itself move in the same direction. So what you have here is you have something called a compression, which is where it's squeezed together a little bit, and then something called rarefaction, where it's thinned out a little bit. So same kind of a video on YouTube where we can see those two things. And here's the compression, and right behind it, here's the rarefaction. Compression, rarefaction. So, if we wanted to see the two of them together at the same time, I could show you both of those together at the same time. And it'd be nice if this looped for longer than 6 seconds here, but maybe if I just keep kind of going back and forth, and then maybe even if I pause it for a second, here's a compression, here's a rarefaction. Here's a crest, here's a trough. So the crest seems to kind of correlate with the rarefaction and the trough. I mean, it's not like ideal like that, but you have a spot where it's together and then thinned out, and you have a spot where it's up and then a spot where it's down. So that is true for the two waves. So here's the deal. How do these things fit together? How does the mechanical wave and the compressional wave fit together with electromagnetic? So how do they fit together? An electromagnetic wave, a wave that does not have a medium, you cannot have a compressional wave that is electromagnetic. You can have a transverse wave. As a matter of fact, all those electromagnetic waves, gamma rays, X-rays, ultraviolet waves, all those are great examples of transverse waves. A mechanical wave, on the other hand, can be longitudinal and it can be transverse. So for electromagnetic, this is the only kind of wave you can have. That's it. There is no other kind of wave that you can have that's electromagnetic. An electromagnetic wave is a transverse wave all the time. Whereas a mechanical wave, some of them can be longitudinal. Longitudinal wave would be a place where they're compressed and then rarefacted and then compressed. And you can also, like a water wave would be a transverse wave. By the way, sound is this kind of wave. So sound is a great example of a mechanical wave. Light is a great example of an electromagnetic wave. And that is what we're going to end up with this year. We're going to talk a little bit more about sound and light. For today, this concludes it. You do have a little bit of a homework assignment to do, so make sure you get that done.